Hey guys, welcome to Malcolm V8. Today we're talking all about heat exchanger fans. So ever since these cars have been out for the last 20 years, there's been an endless debate as to whether you should have fans or not have fans on your heat exchanger. So let's just cover that real quick. First, what exactly is this heat exchanger? Well, it's a big radiator type core, as you can see. Both of these cars have one in it, and its purpose is that it has fluid flowing through it. It cools the fluid down to cool the air intake charge going into the engine, because both of these engines have superchargers on them, and that generates a lot of heat and you need to pull it away. So that's the main purpose of what this heat exchanger is doing in the car. Its job is to extract heat out of the fluid. Now, as you can see, we've got a pair of fans on here, and actually both of these cars have fans on them. And ever since the start of time, people have argued fans don't do anything, and other people say the fans help. And what caught my interest and what made me decide to do this video is more recently, people have started saying not only do the fans not do anything, but they actually make it worse. Yes, you heard that right. Adding fans on reduces the efficiency and makes this thing even worse than if it had no fans on at all. And that's kind of interesting. At first I thought, wow, that's crazy talk. And I started seeing more and more comments coming up, and I started Googling and researching it, and I found there's companies that have a whole entire websites full of information on why that is so. And there's all kinds of science about it. You know, it goes from how little air they pull through and how the fan actually, this big motor section is blocking the airflow coming through, which reduces the efficiency of it and would be better if there's no fan at all. But then there's people that argue, well, the heat exchanger is tucked back in behind your bumper, and the airflow coming through here is not the greatest, so the fans help pull that through. Plus you have a low pressure area because the air scoops over the car and under the car as it's cutting through the air. So there's all kinds of arguments back and forth, and I thought, you know, we could dissect this, you know, all the science and figure it out, but I thought, you know what, let's do this Mythbusters style. We're just going to test it. We're literally going to run a car with and without the fans and compare the values. So we could do one car with and one car without, but I think there's way too many variables to do that. So we're going to pick one car and use the same car with and without fans. So how do we quantify whether the fans are working, helping, or not helping? It gets interesting because over here, on the back of the supercharger and on the back of that supercharger, there's a temperature sensor that measures the temperature of the air going into the engine. They call that the IAT, or air intake charge. That's ultimately what you're trying to cool, but I think that is a very poor way to gauge the performance of the heat exchanger and the fans, and I'll tell you why. Because there's too many variables. As the throttle blade is opening and closing, it's restricting the airflow in there, and it's causing that temperature to go up and down. The heat of the engine and the heat soak of the engine and the amount of heat radiating into the blower and the air intake charge is greatly affecting it. What kind of supercharger you have makes a huge difference. What pulleys you have on here, determining the speed that you're spinning the supercharger, also makes a huge difference. There's so many variables, I just don't like it. It's not a good way to go. I think what we need to do is get the actual temperature of the fluid in the system. So this reservoir right here, this is the fluid reservoir for the supercharger's cooling system, has a temperature sensor in it that it data logs the fluid temps. And at first I thought, well, that's kind of going to be a neat idea, but that has some flaws too. Let's take a look. Okay, so this is the setup of the Red Fire. This is its cooling system. So let me show you what's going on. We have the engine, the supercharger sitting here with the intercooler core, and this is actually the source of all the heat. This is where all the heat comes in from the supercharger and introduces itself to the system. It comes up and flows into the heat exchanger, where we have a fan over here, fans trying to get rid of the heat. And then it flows down to our reservoir, and that's where I was mentioning we have a temperature sensor that's data logging, goes back to the pump and circulates through. So this reservoir here does capture the output of the heat exchanger, but there's other influencing factors. If you look on that engine bay real close, you'll notice that this is very close to the engine and kind of close to the headers. So depending on airflow and movement, for example, when you stop and you're idling, a lot of heat is going to radiate in the system here, and I expect to see this temperature sensor go up some. And that would be artificially telling you that the fans are or are not working. So that's not a very good setup. I mean, we get a good idea of what's going on in the system, but not specifically what's happening here with regards to fans. So for that, what I think we need to do is install a temperature sensor right here and right here. We literally need to capture the temperature of the fluid going into the heat exchanger. We call that heat exchanger 1 and heat exchanger 2, and the fluid coming out. I can't think of a more direct way of measuring the performance of the fans, because that's exactly what the fans are trying to do, is reduce the fluid temperature that's flowing through it. So we can literally just calculate the delta across here, and we can run the car with and without the fans and see what the difference is. Okay, so now that we know we want to capture the temperature going in and out of the heat exchanger, how are we going to go about doing that? Well, I went ahead and grabbed some aluminum pipe, and I went ahead and drilled it and modified it, and I welded a bung inside of it, and I created these little gadgets, if you will. These are temperature bungs on 1-inch pipe. I can insert before and after the heat exchanger, and we're going to go ahead and install these GM temperature sensors right into them, and that way we can capture in and out temperature on the heat exchanger. So at first I thought I'm just going to go ahead and wire these up into the MS3, but I've been adding so much stuff to that car, I pretty much used all the inputs. I didn't have any space to do that. So I went ahead and designed some electronics to capture those temperature sensors. You know, I had some loose electronics laying around with displays I was playing with, and I quite liked the results. So I went ahead and I jumped into the Fusion 360, and I 3D drew a CAD design of kind of like a holder, and then I went ahead and 3D printed it, got it all out and assembled it, you know, put my electronics all on there, and this is basically what I ended up with. So I have the brains of it down here, the microprocessor and Arduino, and it's going to read in my temperature sensors. I'll plug them in over here, and we will have the temperature of the fluid going into the heat exchanger and the temperature coming out, so we can see in real time what's happening with the fluid on there. That works really well, and I was pretty happy with that, and I thought, you know, we could have that up on the dash, we can have a camera in the car, and we can do our testing. And then the more I thought about it was, that's not quite scientific enough. I really do want that in the data logs. It's just going to be so much nicer to overlay and look at things like in the logs. You're going to want to see when you lay into the throttle, for example, there's going to be a delay of the heat going into the system, hitting the heat exchanger, and then the fans or no fans doing their job, and then you can kind of plot that out. So I decided we need to make some modifications. So I went back to my board and I did some more changes, and I added a CAN bus module in here, and that's what these two wires are. These literally wire up to the MS3 through CAN. So the data that we're going to see right here, the temperatures in real time, are actually going to be transmitted through CAN data to the MS3, and they will be in our data logs and on the laptop, just like as though those temperature sensors were wired directly into the MS3. So that's pretty cool. So we'll have, you know, dual displays going on here, and we'll have all the data to look it over. All right, let's see if we can get this guy installed in here without making too much of a mess. We have these all connected up now. Inlet at the bottom, always at the bottom, so that any air in the system can purge and work its way up as normal. Outlet, sensor number 2. It's kind of hard to see, but we got both of them in there, the two sensors. We got a temporary harness that runs all the way up and through into the car. And over here, you can see we got a little digital circuit board. Right now they're both reading around 91 degrees. Pretty cool how that all comes through. And it feeds right into the laptop. Look over there, you can see heat exchanger 1, heat exchanger 2. It's feeding through CAN. I wrote some little CAN control code to interface with that module. Feeds right up, and there it is. Recoding this display halfway through our testing just to make things a little easier to look at. You'll see it says 0F there, 115 on the top. The 0 means that there's 0 delta. In other words, inlet and outlet temperatures are exactly the same. So that way as we're driving, we can just glance and see like a 3, 4, 5, and we know what kind of difference we're getting across the heat exchanger. That's nice. I don't have to do the math anymore. I can just see 4 degrees. Okay, the fans are completely out, and this is gonna go back in now. See what happens. Okay, for this testing, we also have a flow sensor installed in line of our pump that feeds directly into the MS3, so we can tell if the pump is ever scavenging or anything weird's going on and there's no fluid flowing properly that could alter the results of this test. All right, let's talk about the accuracy of our sensors, as that's a question that's probably going to come up, and it's a valid point because our whole test and everything we're doing relies on the accuracy of these sensors measuring the fluid going in and out. So first off, we use genuine AC Delco sensors to eliminate the variance we get on knockoff brands. And then to narrow it down further, I pulled the data sheet online for the sensors, and I found that they had plus or minus 3 degrees variance in the temperature range that we're measuring. So to compensate for that and get our two sensors to line up exactly the same and not have a fluctuation between them, we're going to make changes in the software on our Arduino to correct them. And that gets a little bit complicated, and I just wanted to point out how I did that. So if you plotted a line between temperature and the resistance of the sensor on a temperature sensor, it is not a linear line like this, unfortunately. That would make it so much easier. So if you wrote your code and you said, at a certain point, you were reading 110 degrees on your sensor, but really the fluid was only 100 degrees, so you could just put a 5-degree offset in your code to fix this. The problem is, as the temperature moves up and down, that 5-degree offset now becomes invalid and incorrect, and your sensors start to read way out. And if you have two sensors and you dial them in like that, and you'll see as you cool them down and heat them up, the difference between them is going to move all over the place. So if you go look up an actual temperature sensor, what does its curve look like? It actually plots a curve that looks like that. And initially you think, oh wow, that's unreal. How do you write a formula to work with that? Well, you can look up a formula called the Steinhart-Hart equation. Some really smart guys came up with this in 1968, and they plotted this graph and they wrote an equation that you can use in your code so that you can accurately predict where a temperature sensor's temperature reading will be based on the resistance of the sensor. Now, we're not going to go into all that. It's overly complicated, and if you're kind of a techie guy and you like that stuff like me, go ahead and Google it and experiment with it. I think it's a lot of fun. I'm just simply bringing it up to you guys so that you know that I took the time to work out that equation and put it in my code, and that's what I'm using on my little circuit board I showed you. So when I wrote little offsets in my software to make corrections like this so that both my sensors read exactly the same, as they cool down and as they heat up, they stay exactly in sync because they're using the correct formula. And we went ahead and tested that. We put them in some ice water and let them sit there and freeze down to 32, and we observed both of our sensors going all the way down to 32 and reading that in sync. And then we did the boiling water test and pushed them all the way up to 212, and they were bouncing around 212, 214, thereabout, in a rolling, steaming boil water. So I'm pretty confident our two sensors are going to be in sync and giving us pretty close readings. We may be as much as 1 degree off at times. They kind of fluctuate a little bit, but anything more than a degree is definitely a temperature difference we're accurately reading. And we tested that a lot in our common range as well, 100, 110, 120 degrees. We made sure our sensors were syncing pretty good. So although this is not lab grade quality, I feel like we are extracting the highest quality readings out of the equipment we're using. And drum roll, all the results are in. After months of testing, we've compiled a ton of data, and I'm going to go over it now and show you what's going on. So I drew our little course here that we use to test this, and I'm just going to show you what it is real quick, and it'll help understand the numbers as I'm giving them out to you. Essentially, we start right here, and we take off and we go on this drive. And this initial portion here, it's a mix of, I'd call it maybe country roads. It's not real heavy in traffic. We can cruise up to 50, 60 mile an hour. There are some traffic lights, so you do get some stop and go and cruise along. Then we hit here this green bar. You can see there it's got a 5. That's a period where we pull over on the parking lot on the side and we sit there for 5 minutes. And that can be simulating, getting out and talking to your buddy, sitting in traffic, staging lanes at a track, whatever you want it to be. Pretty common scenario. So we have a 5 minutes sitting there. Then we immediately pull out, and then we hit this blue line. You can see it's the highway. We have a 10-mile stretch where we would just cruise straight in one direction. Average on our logs there is always right around 77, 78 mile an hour. Turn around at the end, and then on the 10-mile stretch on the way back, you'll see we have some red sections here. where we made some pulls. So we slowed down to about 40 mile an hour and then hit it real hard to give us some highway pulls, heavy acceleration and heat, and then of course there's some cool downs or cruises in between those pulls to see how the system recovers in terms of the cooling. And then once we got off of the highway, back into the same kind of roads, and we would hit another spot next to a little private road where we could do another 5-minute stop, sitting there, watch what the system does for 5 minutes, and then immediately from that we'd pull out and do a really hard dig run. Some days we do 0 to 100, some days 0 to 120. The idea was to really load up the system with some heat real hard, and we purposely did it right after sitting there for 5 minutes because we're trying to gauge the difference, with and without fans. After that, then we have some cruising period, and we'd get back here. So each day we did our data collection set for this. The process we went through was start the car up, let it idle up to temperature. Once it was fully up to temperature, we would then go ahead and do this whole entire loop. And that would be one run. And that was nothing but a control run just to completely heat soak the car and get it ready. We would do an actual, that would be now be our first test run, say with fans or without fans. We actually did it both ways on different days to avoid any sort of bias that happens by always testing fan first or always testing no fan first. So we flip-flopped it and alternated it. This whole course takes about an hour to make one loop. We're talking about a 4-hour period of work each day for doing this. So it's definitely took some time, and we did this on and off for about 7 months now, so we have quite a range of data. Now when I'm explaining these numbers, when I talk about the heat exchanger temperature, I'm always talking about the fluid coming into the heat exchanger. And then the delta would be the difference in the cooling. So if 100 degrees came into the heat exchanger and 95 came out, all I'm going to say is we had a 100-degree temperature and a 5-degree delta. So that would tell you there was a 5-degree drop across the heat exchanger. And that's the easy way to go over the numbers. Okay, so now clearly we're not going to go over 7 months of data in detail. That would be terrible. So I've compiled stats and spreadsheets of summaries of all the logs over time, and we'll cover those. Okay, so let's just look at one particular instance. In this case, we're going to look at the 5-minute idle blocks, sitting there idling with and without fans. And with no fans on there, on average, I was seeing a delta of 0.41 degrees Fahrenheit across the heat exchanger. Not much of anything, and I imagine most of that cooling is probably from the engine fan causing a little bit of a draft pulling air through there. However, with fans on full power, full blast, I saw 0.88 degrees Fahrenheit delta average across all of our logs. So still pretty sad. I mean, it's better, but I expected a lot more personally. I mean, it is double, but it's still on average of less than 1 degree of a temperature drop sitting there at idle. However, that doesn't tell the whole story. As I dug in further and started looking at things, I started noticing, for example, the heat exchanger fluid coming in at the start of the 5-minute idle with no fans would be about 109, for example, in one log. And at the end of the 5 minutes, it's now at 117. Another run was 110, 118, and so forth. So you're seeing a climb up there. The whole coolant system is climbing in temperature with the supercharger. However, when you're running fans, I saw much lower rises in the entire system. So although there's only, on average, I would see 1 on my display a lot, but the logs don't lie in the average amount, 0.88 average. The whole system as a whole doesn't heat soak like it does without the fan. So I'd see 105, and 5 minutes later, the fluid coming in is only 106, and other times like 109, 112, and that's pretty typical across just pages and pages of logs. So the fans are keeping the whole entire system a little cooler while you're sitting there idling. And the reason we did the dig run immediately after that is because we wanted to see, does that even matter? What does that help? And also in consideration of that, in that 5-minute idle period, we looked at the actual air intake temperature going into the engine, which of course is MAT, manifold absolute temperature. And the difference is minimal. I'm actually surprised we were able to see the difference, but averaging over all of our logs, talking about the second block specifically, after doing the heavy highway runs and the hard pulls, our average temperatures would be between 153 to 158 IAT2, or air intake temp 2, after the blower. When we had the fans on the system, it would be about 151 to 156. So we're talking like a couple degrees improvement. A few more degrees on the fluid, but the temp is about there. Although idle is not the greatest way to read it, the results are fairly consistent across all of the tests. It's also worth pointing out, these are extremely hot days, upper 80s, lower 90s, very humid. And don't forget, we have a very big blower on that red fire. It's a Gen 5 3-liter Whipple, and we have it pulleyed for about 28.5 pounds of boost in the hottest of summer. We see closer to 30 pounds when the weather cools down. And take into account how much heat soaking and driving we're doing. So if you think these numbers are kind of high, they're actually pretty good. When we start up the car kind of cool and just go for a drive, we see probably 20, 30 degrees lower IAT2s, but we heat soak everything so we can gauge the differences that we're trying to decipher here. All right, this section to me is probably the most exciting and most important of it all. What we've got testing here is the 5-minute idle section to see what effect that has on the cooling system as a whole, the dig run to see how it affects our hard acceleration, and then the cruise on the way back to see how the system recovers. And that little section right there, I think, kind of summarizes a huge portion of what will help people decide fans or no fans. So let's look at it. Okay, we covered the 5-minute idle in the prior section, but essentially, there's the starting temperature from the 5-minute idle, no fans, with fans. Then I picked one particular dig run here where we did 0 to 100. And I wrote down the values here of what we hit at the peak of 3rd gear. Remember, this is a turbo 400, so it's only got 3 gears. Pretty loose stall on the automatic. We hit it 0 to 100. On the setup with no fans, the heat exchanger fluid at the top of 3rd gear before I let out the throttle was 123 degrees. That means the fluid coming into here was 123 degrees. And on the run with the fans, it was only 119. About a 4-degree difference, and you can see they actually started with a 4-degree difference. That exact ratio doesn't hold true through all the logs, but this is a pretty good one. The manifold air temps was 150.3 at the top of 3rd, with fans was 146. So we had a little bit of an improvement there. And just for interest's sake, I went ahead and wrote down what the peak values hit after I let off and was coasting down from speed. The air intake temp, the manifold temp, spiked all the way to 154, and with fans on it only spiked to 149 on that run. And this was the fluid temp, so the heat exchanger fluid spiked all the way to 137 on the inlet, 131 with fans. And then just to have another data set to go over with you, obviously I can't do tons and tons of them, but another interesting example, we did this was like a high 80s day, this was a low 90s day, it was a hotter day. And we ran the car a lot harder here. You can see we pushed it all the way to 116. So we started out at 134 with no fans after the 5-minute idle. Started out at 124, so we had a 10-degree advantage on the run that had fans on it. Hit it 0 to 116. At the top of 3rd gear before I let out, the fluid temp was 141 coming in here, 134 on the run with fans. But look at the IAT2, or the intake air temps. It kind of levels out, and I think it's because we've reached a point where it's just kind of saturated and not getting hot enough. Best I can tell, because I do see this trend across some of the logs where we push it really hard. 164 there, and only 0.2 of a degree improvement despite lower fluid temp and even a lower starting temp. And again, I charted the peaks for you so you could see after I let out, it was kind of peaked, which also is why I think that it's saturated. You can see from 164, it went to 165.6, and here we went to 164.6. So they were kind of maxed out. The fluid temps, kind of interesting, 153 degrees coming into the heat exchanger here at the top of, not at the top of the run, but after I let out the peak fluid temps. And then 150 on this one. So they came very close despite their 10-degree improvement on the start there. And then, you're probably wondering, like, what's the delta across there? So this is on the cruise back after making these runs. So after doing the 0 to 100 run and then letting out and letting the system kind of stabilize for just a few seconds and then cruising this whole way back, these are the deltas across the heat exchanger. In other words, how much it was cooling after 0 to 100 with no fans on there. We were getting an average of 3.2 degrees drop across the heat exchanger at 65 mile an hour was my average speed through all the lights and all the driving on the way back. The run with fans, we're getting 4.3 degrees drop across here. So the heat exchanger, after the heavy run, was doing about half a degree better. Also 65 mile an hour. On the harder run, 0 to 160, you can see we're getting 4.8 with no fans. That was a 60 mile an hour average. 5.4 with fans on there, 64 mile an hour average on the run back. So this, I think, is pretty representative of a lot of these logs kind of summed up, and it kind of helps you see the general trend of differences I was seeing between fans and no fans. Okay, here's another set of data that I find pretty cool. Here is a sample run where we simply started out and we drove the whole entire loop all the way around. No 5-minute stops, no heavy throttle, no pulls. We just want to see what the fan versus no fan does in all different driving conditions, from pulling off 50, 60 mile an hour roads, 40 mile an hour, 30 mile an hour, highway cruising back. Let's take a look. Starting out from home, I broke it down like this. So I didn't want to put overcomplicated with all the heat exchanger, starting and ending temps and everything. This is the average temperature of the heat exchanger, fluid coming into the heat exchanger, the average delta of the temperature drop across it, and the average mile an hour. So for our first cruise all the way around to the highway, in other words, all this country road and traffic lights, no fans, heat exchanger had an average of 110.6 degrees Fahrenheit, fluid coming in. The delta was 2.614. We had an average of 51 mile an hour. With fans, it was down to 105.8, 2.948 delta, 56 mile an hour was the average mile an hour, 0.334 of a degree improvement in cooling of the fluid coming into the heat exchanger. On the highway, this is what I find interesting, because look at our averages here. We're at 77.6 mile an hour, both runs exactly on the spot. Heat exchanger, 112.2, 110.1. The delta, 4.16, 4.403. 0.243 improvement with fans. And this is kind of an interesting one. And we turned around and repeated it on, we did the whole loop twice, coming back on the second run, same thing, 113.1, 112. 4.1 delta, 4.587. Actually did a little better on that second one. 78 mile an hour both times. 0.479 improvement. And the whole premise of the video was that the fans make the heat exchanger worse. They make cooling worse. They break things. And our testing says quite the opposite. That's not true. Myth busted. In fact, you get an improvement. Granted, it's 0.2 of a degree improvement. It's still an improvement, and it's not a failure of the fan. Here it's almost half a degree improvement. So at least for our particular setup, I'm sure this will vary from car to car and heat exchanger setup and so forth, because you got to look at the front of the car where the bumper is, how the air is getting in and so forth. I'm sure it's going to vary greatly per car. On our particular car, an 03 Cobra Terminator with a particular heat exchanger and fan setup we're using, there is no downside to fans, nowhere along the way. Even look at the cruise back after the highway. 112.1 no fans, 108.3 with fans. The delta was slightly improved, 0.18. Granted, that's like minuscule. Mile an hour was 58 and 63 averages for the two going back. Pretty interesting data. All right, guys, that's a lot of data and a lot of information. I hope you enjoyed. I sure have enjoyed putting all this together, and I've sure learned a lot. I hope you have. And of course, the million-dollar question, is it worth having fans on your heat exchanger? And based on all this testing and information, I'm going to say no. I don't think so. If your fans are already on your car, we've shown that it does help a little bit everywhere. But if you don't have fans, is it worth the cost of putting them on? No. Is it worth the weight? Is it worth the electrical load on the alternator? No, I don't think so. That's a tough one for me to swallow. I've invested so much time in fans on these cars. I have fan speed controllers that's set up with the MS3. Based on the fluid temperature, it ramps the fans up and down accordingly to what I need. But in the end, the data doesn't lie. It's not really doing jack. And just FYI, when I ran these tests, I bypassed the fan controller and the fans ran full power the whole time. However, there's one major thing that we haven't discussed and pointed out, and that is, look at how these fans are mounted onto this heat exchanger. I'm gonna call it out and say it's complete garbage. Look at this, I can put my fingers under the fan. Literally, there's space so far away, I can squeeze my finger in there. You know what that means? The fan is just sucking air from the sides. It's not even pulling it through the intercooler. And to make matters worse, there isn't even a shroud forcing suction across the whole entire thing. Anyone who's been a hot rodder or played with cars or engine cooling knows what a huge failure this is and how poorly these fans are performing. Doesn't matter how powerful or how good of a fan you are, and these are small fans, and in my opinion, the best you can get. But they're pretty worthless when they're mounted like this. So I'm kind of curious, do you guys want me to build a shroud, and a proper shroud, and completely seal this off, put the fans on and repeat this and see what happens? See if suddenly the fans become worth it? Or are we just done with fans and gonna toss them and be done? Comment down below and let me know what you guys think. Curious to hear what you guys got to say. Take care, be kind to one another. See you later.